Hi everyone, welcome to this YouTube channel, Best Science Brain YouTube channel. So today we are trying to take a look at May-June 2024 practical physics. The experiment we want to do is based on fluid mechanics as demonstrated by Archimedes. So we are running an experiment on the first instruction or specimen. And then this experiment requires some equipment, which include the rotor stand, then the spring balance, then we also need two liquids. One of the liquids is water, as you can see, while the other one is labeled L, an unknown liquid. So they are contained in two different beakers. Beaker of 500 ml beaker, and the volume of liquid in each beaker is maintained at 400 ml. 400 ml of water in this beaker and 400 ml of kerosene in the other beaker. So you know the moles that you have to use 400 ml. We have to use enough liquid that will submerge the masses they're going to use for the experiment. So apart from this equipment we also have some masses here for the experiment. So we have the 50 gram mass, you can see 50 written on it. We have the 100 gram mass. We also have this one, which is two masses stacked together, 50 gram and 100, making it 150 gram mass. So WAEC did not specify the mass we're going to use, but in this experiment, on this illustration, we're going to use masses of 50 grams, 100 grams, 150, 200, and 250 grams for the experiment. Perhaps you may try your own using 20, 40, 60, 80, and 100. So that is what we need for this particular experiment. So as I said, the two liquids, one is water, and the other one is, that is water. The one is labeled L. We have the rotor stand. On the rotor stand, you have the spring balance hanging on the rotor stand. So look at the spring balance. So we have to understand the reading of the spring balance. The right hand side of the spring balance is in grams. You can see that. You have 0, 25, 50, 75, 100, 125, 150, 175, 200, 225, and 250 grams. While the left-hand side is for measuring weight, newtons. 0 newton, 0.25 newton, 0.50 newton, 0.75 newton, 1.0 newton, 1.25 newton, 1.50 newton, 1.75 newton, 2.0 newton, 2.25 newton, and 2.50 newton. We need to understand how to read the weight, that the newton side, the left-hand side of the spring balance, because that is the utmost importance in this experiment. So how do we read the weight of the spring balance? We see that between 0 and, let's consider the first two digits, between 0 and 0.25. The difference between 0 and 0.25 is 0.25 minus 0 is 0.25. And between 0 and 0.25, there are 5 tiny lines between 0 and 0.25. So how do I know what each line stands for or represents? So I divide 0.25 by 5, and that will give me 0.05. So each tiny line on the spring balance is 0.05. Each tiny line that is on the Newton side, that would mean the weight side, is 0.05. So let's count it and see how it works. So as you can see, let's get the spring balance. Each tiny line is 0.05. The first line after 0 is 0.05. The next line is 0.1, second line. Third line will be 0.15. The fourth line is going to be 0.20. Then the fifth line now becomes 0.25. So you continue adding 0.05, 0.05. So each line on the Newton side that is representing weight is 0.05. So why for the grams, that is the mass side, the right hand side of the spring balance, the first digit is 0, second digit is 25. Difference between 25 and 0 is 25. So what does each line represent? There are 5 lines between 0 and 25. So divide 25 by 5. That gives you 5. So each line on the gram side is 5 grams. So let's count it. After 0, the first line is 5, followed by the second line is 10, third line is 15, fourth line is 20, then fifth line is 25. So having understood the scale of the spring balance, we should know that on the gram side, one line is 5 grams. On the Newton side of the weight, one line is 0.05. Very simple to understand so that you don't make mistake in reading. And then when you read, you avoid error due to parallels in locating your readings. So you see the hook on 0. That hook is called the pointer on the spring balance. So we'll now start the experiment. We'll go to the question that we have provided to assess this experiment on upthrust or fluid mechanics administered by Archimedes many years ago. So we have May, June 2024 practical physics. Alternative A, practical physics. So look at the diagram provided there. The diagram will have a rotor stand, as we have shown you. We have the spring balance hanging on it, the pointer, and then the support above. And then we have that support means the clamp where the spring balance is hanging. Then we have the beaker under it. Then have the object, the mass we're going to hang on the spring balance. The mass I showed you a few minutes ago, 50, 100, 150, 200, and 250. Then that beaker contains water. That's the first diagram there. We'll now move to the other side of it. We see under diagram the same kind, but the difference is that in this second diagram, what the liquid inside the beaker is tag L, while the liquid in the first one is water. So let's go to the instructions and then carry out the experiment. It's a very simple experiment. Question says, study the diagrams above and use them as guides in carrying out the following instructions. Study the diagrams above and use them as guides in carrying out the following instructions. I, using the spring balance provided, determine the weight of object of mass m equal to 50.0 gram in air. Record this weight as W1. I repeat, using the spring balance provided, determine the weight of object of mass m equal to 50.0 gram in air. Record this weight as W1. So we're going to hang the mass of 50 gram on the spring balance, find its weight, and record it as W1. So let's go to the experiment. So go to the experimental setup. So what I'm holding is a mass of 50 grams. Take it up. So amount of 50 grams. You can look at it. The amount of 50 grams. So we're going to hang it on the spring balance. So the mass is hanging freely on the balance. You can see it's not touching the floor. So move up. By means of a thread, it's hanging freely on the spring balance. You can see that. So let's find the weight. You see where the pointer is. So that means the mass is 50 grams. The pointer is at 50. The mass is 50 grams, and the weight on the other side is 0.5 Newton. So this is the mass in air. The mass in air is 50 grams, while the weight in air is 0.50 Newton. Mind you that you must get a spring balance that has gram and Newton on different sides. You have a balance that has only grams. There's some that have only grams. It will work for this experiment. So let's record our W1 as 0.50 Newton. So we'll go back to our table of readings. The serial number for number 1 experiment, we have M, that's the mass. So we're going to record the mass under M as 50.00. We maintain our value to 4 SF, 4 significant figures for consistency. Then we'll go to the next column, that W1, that the weight in air, we obtain 0.5. So record 0.5300, maintaining 4 significant figures. So that is it. For the first experiment, the mass 50.00 grams, weight 0.5300 Newton. So we'll go to the question for the next exercise. Question II says, determine the weight of the object when it is completely immersed in water contained in the beaker as shown in the diagram above. Record the weight as W2. I come again. Determine the weight of the object when it is completely immersed in water contained in the beaker as shown in the diagram above. Record the weight as W2. The diagram is this one. And if you look at the diagram very well, the mass is submerged. The mass is below the water surface, totally submerged. And also, you also notice that the object is not touching the wall of the beaker. The object is hanging freely, floating in the water. So it's submerged below the water surface, and then it's not touching the walls of the beaker. Neither is it resting at the bottom of the beaker. So you have to take these precautions. So we'll go to the experiment. So we can see the mass of 50 grams immersed inside water. Check very well. Look at the water surface, the minuscule of water. And look, and you see that the mass is resting or floating below the water surface. So completely immersed inside water. And also if you go down, you see that the mass is not touching the bottom of the container. Neither is it touching any part of the container. So these are the precautions we have to take. So we'll now go to the spring balance and read. Find the reading okay, you can see that the pointer is around, after as I told you, our interest is the weight, W2. We're reading the weight, the Newton side. And I told you that one line on the Newton side is 0.05. So when we read it, after 0.25, the next line is 0.3, followed by 0.35, and then 0.4. So the pointer is approximately at 0.4 Newton. So that's the apparent weight of the 50 gram mass when immersed inside water. So we record the weight W2, the weight in water as 0.40 Newton. So we'll go to our report. So we'll go to the column for W2, that the weight in water, and record 0.4300 to maintain the value for consistency. Maintain the value to 4 SF. You can see maintain your value to 3 SF, but be consistent in your recording, please. So go to the next question. Question III says, determine the weight of the object when it is completely immersed in the liquid L, record the weight as W3. Determine the weight of the object, which object, that the 50 gram mass, when it's completely immersed in the liquid L, record the weight as W3. So the second diagram shows the object in a liquid L. So we're going to perform the experiment now. And before we perform the experiment, we need to clean the mass, clean that mass, so that water will not contaminate the liquid L using a neat material. So as a precaution, as I said, we need to clean the mass and make it free from moisture with a neat material. So after measuring or find the weight of any mass, whether in water or in liquid L, you have to clean it before you dip it into another liquid. So that's a precaution that you maintain as to achieve accuracy in this result, or in this experiment. So we'll now move over to put the mass in the liquid L. Remember, the water has been removed. So that's why the pointer returned to 0. There's no weight hanging on the mass again. Pointer returned to 0. So we can see the 50 gram mass hanging inside the liquid L, hanging inside of it, submerged, completely submerged. So under the liquid. And also you also find out that the mass is not touching the container, the bottom of the container, or any part of the container. So let's take a reading from the spring balance. From the spring balance, you see where the pointer is. So the pointer, okay, let's read it. So the pointer is, get it right, please, is, so let's read it accurately. Okay, at the Newton side, after 0.25, the first line is 0.3, then 0.35, 0.4. The pointer is between 0.4 and 0.45. You can see it clearly, between 0.4 and 0.45. So since one line is 0.05, so since the pointer lie at the middle, divide 0.05 by 2, you're going to have 0.025. And then the line before the pointer is 0.4. So I'm going to add 0.025, that the mid value, to 0.4, and that give me 0.425. 0.425. That's the reading of the pointer when the 50 gram mass is immersed in the liquid L. So let us record our reading, 0.425. So come to W3, which is the weight or the apparent weight in the liquid L, 0.425, and record it, 0.4250, maintain to 4 SF. So the apparent weight in liquid L is 0.4250 to 4 significant figures. 0.425. So let's go to the next question. Question IV says evaluate U equal to W1 minus W2. U equal to W1 minus W2 and V equal to W1 minus W3. So that U stands for the upthrust in water, and that V stands for the upthrust in the liquid. Remember that W1 is the weight in air and W2 is the weight in water. W3 is the weight of the substance in liquid L. So let's go and fill the space in the table. So the column for U, W1 minus W2. W1 is 0.5. W2 is 0.4. So 0.5 minus 0.4 will give us 0.1. So the upthrust in water is 0.1302, making it to 4 SF. Then the upthrust in liquid L, that is V, which is W1 minus W3. W1 is 0.5. W3, the weight in the liquid, is 0.425. So 0.5 minus 0.425 give us 0.075. So here we record 0.07500. So summarizing our first experiment, the mass we weighed was 50 grams, 0.00. On the spring balance, the weight is 0.5000 Newton, that is to 4 SF. Then that the weight in air. Then the weight when immersed in water, the apparent weight in water is 0.40 Newton, written to 4 SF. Then the apparent weight when immersed in a liquid L is 0.4250 to 4 SF. Then the upthrust in water with W1 minus W2, which is 0.5 minus 0.4, giving us 0.100. Then the upthrust, that is V, when immersed in liquid L, W1 minus W3 will now be W1 is 0.5, W3 is 0.425. So 0.5 minus 0.425 gives us 0.07500 to 4 SF. So that summarizes the first experiment. We'll now go to the next question. So the next question, question V, says, repeat the procedure with the objects of masses M equal to 100 gram, 150 gram, 200 gram, and 250 gram. Then VI says, in each case, evaluate upthrust in water, which equal to W1 minus W2, and V, upthrust in the liquid, W1 minus W3 for each of them. Then VII say tabulate your readings. So we're going to repeat the same procedure that we made for the 50 gram mass. We're going to start with the 100 gram mass. Now after the 100 gram, we'll go to 150 gram, 200 gram, until we reach 250 gram. And do everything we did for the 50 gram mass. We're going to repeat it for these other masses. Okay, so let's go to the experiment. So we have a 100 gram mass hanging freely in air. You can see the 100 written on its body. 100 gram mass hanging freely in air without touching any material or touching the base of the rotor stand. We'll now move up and then find out its weight on the spring balance. So look at the spring balance. The mass is 100 grams and the weight is 1.0 Newton. The mass on the right hand side, 100, you can see where the pointer is, and the weight 1.0 Newton. So you can see that clearly. So we'll go over to the experiment. Now we're going to immerse the 100 gram mass inside water and find the apparent weight in water. But before we do that, we have to record the 100 gram on our table of values, and the weight 1.0 on the table of value before we go on to immerse it inside water to find W2. So go to the second column, number 2 experiment. The mass we are weighed is 100 gram. We have 100.0 to 4 SF, and the weight, which is our W1 in air, is 1.0. We now have 1.000, making it to 4 SF, making our readings consistent. Your reading should be consistent. Whether you're using 4 SF or using 2 decimal places, make it consistent, please. 1.000. So that is it in 4 SF. So we're going to now immerse the 100 gram mass inside water and find our W2, which is the weight in water. So we can see the 100 gram mass hanging freely in water. Look at the base of the beaker. It's not touching the beaker, neither is it touching the wall of the beaker. And also it's submerged under the water surface. So let's move up to the spring balance and then find the weight on the spring balance. So you can see where the pointer is. So the pointer, remember that we are reading on the left hand, we think the reading on the left hand side of the weight. And then we know that each reading on the Newton side is 0.05. So after 0.05, the next line is 0.8. Then the next line is 0.85. So it's approximately 0.85. So 0.75, add 0.05 to it, add 0.8, add another 0.05, you have 0.85. So that is the apparent weight in water, approximately 0.85 Newton. So record our weight on the record sheet. So go to the second column, 100 gram mass. We are now going to the third, that is W2, the weight in water, which you got as 0.85 approximately. So now right here, 0.8500 to 4 significant figures. So having done that, the next is we're going to immerse the 100 gram mass inside the liquid L, and find the apparent weight, which is W3 in liquid L. Before we do that, we have to clean the mass, clean it off, remove the moisture or the water on it by using the white material we're using. We'll clean it off, make it dry before we immerse it in the liquid L to find our W3. So we can see the 100 gram mass well below the surface of liquid L, but not touching the bottom or any side of liquid L. It's fully submerged. So we move up to find the reading of the spring balance. You can see where the pointer is located. So the pointer is located, well, remember that our focus is on the Newton side. The pointer is located between the second value after 0.75 and the third value. So they read it. Since the Newton side, one line is 0.05. So after 0.75, the first line there is 0.8. Then next line is 0.85. So it's located between 0.85 and 0.9. So what do we do? Since one line is 0.05, we divide it by 2. That gives us 0.025. The reading before the pointer is 0.85. So as I said, its reading lies between 0.85 and 0.9. After 0.75, the next line is 0.8. The other one is 0.85. The pointer is between 0.85 and 0.9. So since one digit on the Newton side is 0.05, divided by 2, you have 0.025. And the reading before the pointer is 0.85. So I'm going to add 0.025 to 0.85, and that gives us 0.875. So that approximate weight of the 100 gram mass in the liquid L. Okay, so let's report our work. So on our report sheet, we'll now go to W3. So W3, that is the weight, or the apparent weight of the 100 gram mass inside liquid L is 0.875. So report 0.8750, value to 4SF. So having done that, We'll now go to upthrust. That W1 minus W2, the upthrust in water. W1 is 1.00, W2 is 0.85. So 1 minus 0.85. So that becomes the upthrust in water will give us 0.15. So here we have going to write 0.1500 to 4 SF. That is the upthrust of water, of the solid in water. We'll now go to the next column, V. That V is the upthrust of the solid in the liquid L, W1 minus W3. So our W1 remains 1.00, W3 is 0.875. So W1 minus W3 is 1 minus 0.875. That will give us 0.125. So that gives us 0.125. So I come here and write 0.1250. 0.1250 to 4 SF. So let's summarize what we have for the 100 gram mass. The weight in air for the spring balance is 1.0 or 0.000 to 4 SF. The weight when immersed in water, or the apparent weight in water, is 0.8500 to 4 SF. The weight when immersed in the liquid L is 0.875, at the back to 4 SF. The upthrust, which is the weight in air minus weight in water, W1 minus W2, that is 1 minus 0.85 will give us 0.15. The upthrust in the liquid L, V, which is W1 minus W3, which is 1 minus 0.875, gives us 0.125, 0 to 4 SF. So we'll now go to the next mass, which is 150 gram mass, the third experiment. 50 gram mass hanging freely in air is not touching the retort base, and then we'll have two masses there making 150. The bigger mass is 100, the smaller mass is 50, giving us 150 grams. So move up to the spring balance and find the weight. So you can see is approximately at 150 grams, and then that is the mass, while the weight is 1.50 Newton. 1.50 Newton approximately. 1.50 Newton. So that's the weight of the 150 gram mass. So let us record our reading before we start immersing it inside water. So the weight in air is W1, 1.50 Newton. So number 3, the mass we are dealing with under mass column is 150 grams. So we're going to write 150.0 here to make it to 4 SF. And the weight from the spring balance is 1.5 Newton. Under weight W1, the weight in air, we write 1.500 to make it to 4 SF. 1.500 Newton, the weight in air. We'll now go to W2. W2 is going to be the weight, the apparent weight when immersed in water. The weight when immersed in water. So we're going to do that now. See the 150 gram mass hanging freely inside water. The two masses 50 and 100, making 150, and not touching the container or bottom of the beaker. So we'll now move up to find its apparent weight in water, that is W2. You see where we have the pointer. The pointer is on the first line under 1.25. I will know that one line on the weight column is 0.05. So you add 0.05 to 1.25, that gives us 1.3. So the apparent weight of the 150 gram mass in water is 1.30 Newton. So let's record our work. So go to W2 column, which is the weight in water, and we'll have 1.3 for the 150 gram mass. So right here, 1.300 to make it to 4 SF. 1.300. So the next, we'll find the weight. W, that is the weight of the 150 gram when immersed in the liquid L. Before we do that, we have to first of all clean up the mass before we now immerse it in liquid L with a neat material. So we can see the 150 gram mass hanging freely inside liquid L. Is beneath the liquid L surface and is not touching the bottom of the container, neither is it touching the wall of the container, it's floating freely. So we'll now move up to the spring balance and read the weight. So you look at the weight, the pointer appears to be on the second line after 1.25. So the first line, if you read, each line is 0.05. So 1.25 followed by 1.3. Other than that 0.05, now I have 1.35. 1.25, 1.3, and then 1.35. So the apparent weight of liquid L, of the 150 gram liquid L, is 1.35. So let us record our work. So we'll go over to the reading. W3, the weight of 150 gram mass in liquid L is 1.35, as we read from the spring balance. So right here, 1.350, making it to 4 SF. 1.350. Go to the next column. Next column says find the upthrust in water, which is U, W1 minus W2. The upthrust, W1 is for the 150 gram mass, W1 is 1.5. Then W2 is 1.3. So 1.5 minus 1.3 will give us 0.2. So our upthrust will be 0.200 to making it to 4 SF. The next, we'll find the upthrust in the liquid L, that is V, which is W1 minus W3. So let's get it. Our W1 is 1.5. Alright, let's crunch it. Yeah, W1 is the weight in air, 1.5. Then W3 is the weight in liquid L, which is 1.35. So we're going to subtract 1.35 from 1.5. So 1.5 minus 1.35. Let's use a calculator and get it right. 1.5 minus 1.35. Give us 0.150. So we'll go over there and write 0.15. Then 0.0 to make it to 4 SF for consistency. So let's summarize what we have for the 150 gram mass. The 150 gram mass, the weight in air, W1 is 1.5 Newton. The weight in water, the apparent weight in water, W2 is 1.300 Newton to 4 SF. The weight in liquid air, W3 is 1.350 Newton. The upthrust in water, W1 minus W2, which should be 1.5 minus 1.3 is giving us 0.2000. The up thrust in liquid L, V, W1 minus W3, which should be W1 is 1.5 and W3 is 1.35. 1.5 minus 1.35 gives us 0.15. Then double 0 to 4 SF. So go to the next mass, which should be the 200 gram mass, the fourth experiment. So here we have the 200 gram mass hanging freely in air. You can see it's not resting on any metal. It's not resting on the base or rotor stand. It's hanging freely. We want to find the weight in air. So we have two masses there. Each of them is 100 gram each, giving us 200 tied together. So move up to find its weight on the spring balance. So on the spring balance, the weight is roughly at 2.0 Newton. 2.0 Newton, you can see it there. 2.0 Newton, 200 gram on the right hand side, 2.0 Newton on the left hand side, which is the weight. Okay, record our work. So on the fourth column, we are now working with a mass of 200 grams. We now have 200.0, which is written to 4 SF, that the mass, and the weight in air from the spring balance, which is at W1, is 0.2. We now write here 0.2300 Newton to 4 SF. So next, we're going to find the weight in water, which is W2. We're going to immerse the 200 gram mass inside water and find its apparent weight when fully immersed in water. So move to the experiment. So we can see the 200 gram mass inside water, the mass floating in water. You see the two masses, 100 grams each, giving you 200 grams, not touching the beaker, and neither is it touching the bottom of the beaker, hanging freely in the beaker and under the water surface. So let's go and find out the weight from the spring balance. You can see the pointer. The pointer is roughly at 1.75 Newton. The weight, you're taking the reading on the left hand side, that is the weight in Newton, not the mass. So 1.75 Newton. The 200 gram mass weighs 1.75 Newton in water. So let's record, and that's a W2, the apparent weight in water. So let's record our reading on the record sheet. So coming to the record sheet, we are trying to now record the weight W2, the apparent weight of the 200 gram mass in water, and we got 1.75 Newton. So we now have 1.750 to 4 SF. So that the weight in water, 1.750 Newton, the weight inside water. So the next we're going to do is to find W3. W3 Newton is the weight or the apparent weight in the liquid L. So we're going to do that. And then before we do that, we have to first of all clean up the 200 gram mass before we immerse it in liquid L to avoid contaminating or changing the density of liquid L. So we can see the 200 gram mass inside liquid L. So take it very well. It's full of mass. The mass is not touching the container. Neither is it touching the So here we are. We're going to record the reading of the 200 gram mass, the weight or the apparent weight in liquid L, W3, and we got 1.8. So go down there, the column there, we'll write 1.8. So we need to write 1.800 to make it 4 significant figures. So that's how consistency in our reading. 1.800. You can see that. So having done that, we'll now go to the next column that says find U, that the upthrust in water, W1 minus W2. So go back. W1 is the weight in air. For 200 gram mass, the weight in air is 0.20 Newton. The weight in water is 1.75 Newton. W1 minus W2. The error in this, correct? The weight in air is not 0.2, it's a mistake. The weight in air we got is 2.00. Sorry for the error. That's what we got. It's a mistake. So the weight in air is 2.00 before SF. 2.000 Newton. While the weight in water is 1.75 Newton. So this 2.0 is at W1, 1.75 is at W2. Up thrust, the U is 2 W1 minus W2, that is 2 minus 1.75. So 2 minus 1.75 gives us 0.25. Give us 0.25. We can record under U 0.25. 2500 to 4SF. So having done that, we also find V. That V is the upthrust in the liquid L, and V is W1 minus W3. W1 minus W3. W1 is the same weight in air, 2.000. W3 is the weight in the liquid. That W3 in the liquid L, which is 1.800. So we find the difference. 2 minus 1.8. 2 minus 1.8 will give us 0.2. So record here 0.200 to make it to 4SF. So for consistency sake, 0.200. So you see that. So let's summarize our result for the 200 gram mass. The weight in air, W1 is 2.0 or 000 to 4SF. The weight when immersed in water, or the apparent weight in water, is 1.75. 0 at the back to make it to 4SF. The weight when immersed in the liquid L is 1.8 or 1.800 to 4SF. The upthrust, the U, W1 minus W2, the upthrust in water, W1 is 2.0. Then W2, the weight in water, is 1.75. So 2 minus 1.75 will give us 0.2500. Then the upthrust, that is V, the upthrust in the liquid L, which is W1 minus W3, is going to be, W1 is 2, while W3 is 1.8. So 2 minus 1.8 gives us 0.2300. So go to the next experiment, or the last one, that involves 250 gram mass. 250 gram mass. Mass hanging freely, as you can observe it from the strain balance. I want to find the weight in air, which is W1. You can see 3 masses tied together there. The bigger masses are 100 gram each, the first 2, if you come from your left, while the smaller mass is 50 gram, giving us 250 gram masses, or gram mass rather. Then let's move up gently to the spiral spring to find the weight. So at the spring, you see that on the left hand side of the spiral spring, the weight is roughly 2.5 Newton. 2.5 Newton. 2.5 Newton. So let's record our weight on the report sheet. So number 5, the mass is 250. 250.0. Okay. Then the weight from the spring balance is 2.5. 2.500 significant figures for consistency. So next we're going to do, that is our W. This is our W1, the weight in air. The next we're going to find our W2. W2 is the weight when immersed in water. The weight or the apparent weight when immersed in water. That's W2. So go to the experiment. So you can see the 250-gram mass hanging inside water. The three masses, the first two 100 and 100 each, and the smaller one 50, that is 250. So if you watch very well, they are not touching the beaker, neither are they resting on the bottom of the container. They are floating freely in the water. Then we move and look at the surface. It's beneath the surface of water. That means it's completely immersed in water. We now move to read our spring balance. So from the spring balance, we can see that the 250-gram mass, look at where the pointer is. The pointer is on the third line below 2.0. Third line beneath 2.0. Remember that you are reading, your focus is on the left hand side, that is the weight in Newton, not on the mass. So the third line, which is 2.0. So if you look at this, how do you count? We say that each digit on the third column on the left hand side is 0.05. 0.05. So after 2.0, we have 2.05. After 2.05, the second line, we have 2.1, continue adding 0.05. The third line, you have 2.15. 2.15 is the approximate apparent weight of the 200 gram in water. 2.15. So let's record our work. So we'll go to the reading to record our W1, meaning the weight. Our W2, meaning the weight in water, the apparent weight in water, which you got from the spring balance as 2.15. So we'll here record 2.15, then 0 to make it to 4 significant figures. 2.150, that is the apparent weight of the 250-gram mass inside water. So next we're going to find our W3. W3 is the weight or the apparent weight when it's immersed in liquid L. The weight when it's immersed in liquid L. So let's go and do that experiment now without waste of time. So as you can see, the weight is hanging freely inside the liquid L and not touching the glass and not resting on the bottom. If you move up, you see that it is submerged under the water, under the liquid surface. So liquid L, this is L, not water, please. So we'll now move up to get our W3, which is the apparent weight in liquid L. When you go up, you see that the pointer is resting between, okay, let's look at it. After 2.0, remember you are reading the weight. The weight is the values on the left hand side of the spring balance. The pointer is resting between the fourth line after 2.0 and 2.25. So let's read it. One value, one line is 0.05. So 2.0, the next line is 2.05. The next one is 2.10, adding 0.05 continuously. The other one is, let's start from beginning again. The first line is from 2.0, the first line following is 2.05. Next line is 2.10. Third line 2.15. Fourth line 2.20. Okay, it's on the fourth line. It's on fourth line. Fourth line 2.20. 2.20, exactly where it is. So 2.20, that's why the pointer is. So that represents our W3. So we'll go on to record our work. So we'll have W3 to record. That is the apparent weight in liquid L, which we got as 2.20. So we'll now write the value 2.200 to written to 4 SF. 2.200 written to 4 SF. So we're now going to find the next column U, upthrust in water, which is W1 minus W2 for the 200 gram mass. Our W1 is 2.5. Our W2 is 2.15. So do some little mathematics here. 2.5 minus 2.15. And that will give us 0.35. So record here 0.3500 to 4 SF. So that's the upthrust in water. We'll now find V, the next column. V, W1 minus W3, the upthrust in the liquid L. Our W1 is 2.00. Our W3 is, what is it? Okay, our W1 is 2.50. Our W3 is 2.2. So we'll have 2.5 minus 2.2 W3, and that gives us 2.5 minus 2.2 gives us 0.3. So 0.3, we'll have it 0.3, but this time around 300, making it to 4 significant figures. So we have done the total experiment involving the 5 masses provided: 50 grams, 100 grams, 150 grams, 200 grams, and 250 grams. Are the masses. Then the weight from the stream balance, weight in air, for the 50 grams, 0.50 Newton. For the 100 grams, 1.0 Newton. For the 150 gram mass, 1.50 Newton. For the 200 gram mass, 2.0 Newton. For the 250 gram mass, 2.50 Newton. Then we now immerse each mass inside water, complete inside water. We'll find the weight in water, W2. We have 0.4 Newton for the 50 gram mass, 0.85 Newton, the apparent weight for the 100 gram mass when immersed in water, 1.3 Newton for the 150 gram mass when immersed in water, that the apparent weight, 1.75 gram Newton for the 200 gram mass when immersed in water, 2.15 Newton, which is the weight, apparent weight of 250 gram mass when immersed in water. The next, according to the instruction equation, we have to find W3, that is the apparent weight when fully immersed in liquid L. So liquid L will have a 0.4250 Newton for the 50 gram mass, the apparent weight, 0.875 Newton for the 100 gram mass, 1.35 Newton for the 150 gram mass, 1.80 Newton for the 200 Newton mass, 2.20 Newton for the 250 gram mass. After I had done all this, they went to find upthrust. Upthrust in water, that's U, W1 minus W2, in Newton. Weight in air minus weight in water. For the 100 gram mass, we got 0.110 Newton. For the 50 gram mass, 0.10 Newton. 100 gram mass, 0.15 Newton. 150 gram mass, the upthrust in water, 0.20 Newton. 200 gram mass, 0.250 Newton. 250 gram mass, 0.350 Newton. They will find the upthrust in the liquid L, that is V, W1 and W3 for each of the masses. For the 50 gram mass, we obtain 0.075 Newton. For the 100 gram mass, 0.125 Newton. For the 150 gram mass, 0.150 Newton. For the 200 gram mass, 0.20 Newton. For the 250 gram mass, 0.30 Newton. And be careful of the column. Each of the column must have a unit. Mass unit given to us from the stream balance is gram. Weight, W1, W2. Upthrust, W1, that is the weight in air. W2, the apparent weight in water. W3, the apparent weight in liquid L. Upthrust in water, U. And the upthrust in liquid, V. All these have the same unit as Newton because they are forces. Okay, so let's go to the next thing in the question paper. On the question paper, please. VI says tabulate your readings, and we have done that already. VII, okay, that's VII says tabulate your readings, we have done that. Then VIII says plot a graph with V on the vertical axis, known as ordinate, and U on the horizontal axis, known as abscissa. Plot a graph of V with V. That V is the upthrust in the liquid L on the vertical axis, that the ordinate, and U on the horizontal axis, which is known as the abscissa. U is the upthrust in water. So then IS says determine the slope of the graph. So before we continue now, we're going to plot the graph. We'll process the readings first and then plot the graph before we find the slope and continue with the other questions following. So if you are seeing this channel for the very first time, for watching this video for the very first time, kindly subscribe to the channel. How do you subscribe? As the video is playing, you're going to see a subscription button like a tiny bell. Under the video, you have the YouTube name, Best Science Brain. Then under the YouTube name, you're going to see a subscription button. There is a bell, a tiny bell. Tap on the bell only once and get subscribed to the channel. So let's go to the graph and then see what we'll have. We now have our process experimental result. Before I go to the graphing, let's go through the table once more. Experiment number 1, serial number 1, have a mass of 50 grams. Then W1, the next column in Newton, which is the weight in air, given us 0.5 Newton. W2, the third column, which is the weight when fully immersed in water, that gives us 0.40 Newton. W3, that is in Newton also, which is the weight when fully immersed in the liquid L, and that gives us 0.4250 Newton. Then the next column, U, which is the upthrust in water, W1 minus W2. W1 is 0.50 Newton, W2 is 0.40 Newton. So 0.5 minus 0.4 gives us 0.10 Newton. Then V is the upthrust in the liquid L, which is W1 minus W3, the weight in air minus weight in the liquid L. W1 is 0.5. W3 is 0.425. So 0.5 minus 0.425 gives us 0.075 Newton. Going to the scum mass of 100 grams, serial number 2, experiment number 2. Weight in air is 1.0 Newton. Then W2, 0.85 Newton, which is the weight in water, apparent weight in water. W3, the apparent weight in liquid air, 0.875 Newton. Up thrust in water, W1 minus W2, which is 1 minus 0.85, giving us 0.15 Newton. V, up thrust in liquid L, W1 minus W3, which is going to be 1 minus 0.875, that gives us 0.125. Going to experiment number 3, we had the mass of 150 grams, the weight in air, which is 1.5, W1, 1.5 Newton, the weight in water, that the apparent weight in water, 1.30 Newton, that W2, W3, the apparent weight in liquid air, 1.35 Newton, the up thrust in water, that is U, W1 minus W2, which is 1.5 minus 1.3, giving us 0.20 Newton. V, which is the up thrust in liquid air, W1 minus W3, which is 1.5 minus 1.35, and that gives us 0.150 Newton. We go to the fourth experiment. Using a mass of 200 grams, the weight in air, W1 is 2.0 Newton. The weight in water is 1.75 Newton. That's the apparent weight in water, W2. W3, the apparent weight in liquid air, 1.80 Newton. The up thrust in water, W1 minus W2, is 2 minus 1.75, that gives us 0.25 Newton. Then V, which is the apparent weight, the up thrust in liquid air, that is V, we got is 0.20. How do we get it? That W1 minus W3, W1 is 2 and W3 is 1.8, so 2 minus 1.8 gives us 0.2. Then the last experiment, that is 250 grams, we use the weight in air, W1 is 2.5 Newton. The weight in water, W2, the apparent weight in water is 2.15 Newton. Then the weight in liquid L, the apparent weight in liquid L, W3 is 2.2 Newton. The up thrust in water, which is W1 minus W2, W1 is 2.5, W2 is 2.15. So 2.5 minus 2.15 give us U as 0.35 Newton. V, the up thrust in liquid L, which is W1 minus W3, W1 is 2.5, W3 is 2.2. So 2.5 minus 2.2 gives us 0.30 Newton. All readings are recorded to 4 significant figures for consistency, precision, and accuracy. So having done that, we observe the readings. They look at the weight in air, 0.5 Newton, 1.0 Newton, 1.5 Newton, 2 Newton, 2.5. So the weight is increasing. The weight in air increases as the mass increases. The weight in water, W2, the apparent weight in water also increases as the mass increases. The apparent weight in the liquid air increases 0.25, 425, 0.875, 1.350, 1.80, 2.20 as the weight also increases. Then the same applies to the up thrust in water U, 0.1, 0.15, 0.20, 0.25, and 0.35 increases. And also the apparent in liquid L, V, also increases as the mass increases, as you can observe. So having done that, we also notice that W2, which is the weight in water, look at the weight in water, W2, and look at the column for weight in liquid L, W3. is that the weight in liquid L is higher than the weight in water. So the apparent weight in water, we have the first column for 50 grams, 0.4, and then there are for the liquid L, W3 is 0.425. Then the second column, 0.85 for the 100 gram mass, and then 0.875 when in mass in liquid L, 1.30 Newton for the 150 gram mass, and then 1.35 when the 150 gram is mass in liquid L, then 1.75 gram for the 200 gram mass in water, and then 1.80 gram for the 200 gram when in mass in liquid L, 2.15 Newton for the 250 gram when in mass in water, and 2.20 gram when in mass in liquid L. So you see that the apparent weight in liquid L is higher compared to the apparent weight in water. So the values of W3 are higher than the values of W2. So what does it make? What do we deduce from here? So we can deduce that liquid L has a lower density than water. Liquid L has lower density than water, or liquid L is more viscous than water. So let us go to the graphing. So the question again says VII, plot a graph with V. That V is the upthrust in liquid L on the vertical axis. The vertical axis is also known as the ordinate, and U on the horizontal axis. So the horizontal axis is also known as the abscissa. And then you know that V represents the upthrust of the liquid, of the object in the liquid L, and U is the upthrust in water. So let's go to the graph right now. So for the graph, we have to choose a scale of 2 cm to 0.05 unit on both axes. 2 cm to 0.05 unit on both axes. So this is a standard graph. Each bus is 2 centimeters. So you can see the scale on the vertical axis, 2 cm to 0.05 unit. So you have the origin 0, 0.05, 0.10, adding 0.05 continuously, 0.15, 0.20, 0.25, 0.30. We stop at 0.30. This is the V axis. That is, the vertical axis, we are plotting V in Newton. So we stop at 0.30. Why? Let us look at the readings and see why we stop. The maximum value is 0.30. So look at the values of V. The vertical axis, the least value is 0.075. The highest value is 0.30. So you see why the vertical axis, we started from 0.05 on the graph and then ended at 0.3 with the maximum value on the V or on the vertical axis. So let's go to the horizontal axis. We maintain the same scale for the horizontal axis because the readings of vertical and horizontal are similar. So you can see 0.05, 0.10, 0.15, 0.20, and then 0.25, and finally 0.30. Okay, the final reading there is 0.35, and you have U, the unit in bracket Newton. So let's go to the table and see why we have to take the scale to 0.35. So look at the values on the U column, ranging from 0.1 to 0.35, 0.1 to 0.35. So you see that the readings fall in with the values we have. The readings are in agreement with the values we have. So although the values of the upthrust in water are a little bit bigger than the upthrust in the liquid L, but the values are similar to each other. So we chose the same scale, 0.05 to 2 cm or to 1 big boss on both axes. So before we plot the graph, we need to understand the scale. Since both axes have the same scale, so we need to understand what does one tiny line represent. If you look from 0 to 0.05, there are 10 lines in a boss. So to know what one line represents, divide 0.05 by 10. So one line represents 0.005. One line is 0.005. So if you look at it, there are 10 lines. So if one line is 0.005, multiply 0.005 by 10, that gives you 0.05. So on both axes, one line is 0.005. So we'll go to the graph now. So we'll start plotting now. When V is 0.075, U is 0.1. When V is 0.075, U is 0.1. So we'll go to the graph. So we have to locate 0.075 on the vertical axis. So you can see 0.05 there. The next line will give us after 0.05, give us 0.055. The next line, second line, give us 0.06. The third line, 0.065. The fourth line, 0.07. And then the next one, 0.075, where you have that pencil dot. 0.075, that is this point. Okay, that location. Then we'll go to the horizontal axis. We'll do for where U is 1. So you can 0.1, that is U, 0.1. You move up. And then that's where you have the intersection. And then you mark yours asterisk. That's the first plot. For the second plot, when V is 0.125, U is 0.15. When V is 0.125, U is 0.15. So let's go to the graph. So let's locate 0.125 on the vertical axis. So as you can see, have this point as 0.1. Next two lines is under 0.01. Since one line is 0.005. So if you can't see two lines, next two lines is 0.1, 0.01, that is 0.11 now. And that two lines, 0.12. Then the next one, where you had the pencil, is 0.125 on the vertical axis. We move to the horizontal axis and locate 0.15. That is there. You trace it up, and this is where they intersect. You mark your asterisk there. So go to the third plot. When V is 0.15, U is 0.2. When V is 0.15, U is 0.2. So go to the graph and plot. So you can see that 0.15 is already in the scale there on the vertical axis. For V, we'll now locate 0.2 for the horizontal axis. So let's move. We'll have 0.2 there. For the out of the line, let's be sure that is 0.2. You see 0.2. So 0.2 merges with 0.15. So the fourth plot, when V is 0.20, U is 0.25. When V is 0.20, U is 0.25. So go to the graph and do the plotting. So you can see 0.20 on the vertical axis, and it happens that the 0.20 is already on the scale. So that is for V. And then U is 0.25. So So we'll move and see where the point lies. You can see 0.25 dot there. We'll move down. We'll have to confirm 0.25 merging with 0.20 on the vertical axis. Then the fifth plot, when V is 0.30, U is 0.35. 0.3 on the vertical axis, 0.35 on the horizontal axis. So let's go to the graph. So you have 0.30 on the vertical axis for V. Then move it to locate 0.35 for horizontal axis. So you see this point, that where they merge, will come down and confirm 0.35. You can see that. So the most important thing is to select a proper scale, and then make sure the scale you select will cover at least 3/4 of the graph. Look at the size of our graph. Will cover at least 3/4 of your graph sheet. And also, whatever you are plotting, you must put the unit of what you're plotting, U in Newton. I didn't write only U. And then V also in Newton on the other side. And mind you, you can also be plot, here I'll plot a V against U. You can also be asked to plot U against V. That is putting U on the vertical and then putting V on the horizontal. It's also a relationship. Okay, so let's go to the other questions. Question IS says, determine the slope, otherwise known as gradient of the graph. Determine the slope or gradient of the graph. To find the slope of the graph, we have to draw a right angle triangle. This is a straight line graph connecting the first point that corresponds to 0.30 on the vertical axis to the last point on the graph that corresponds to 0.075 on the vertical axis. So how to draw a straight line, a right angle triangle connecting the first point, the last point there, and the first point. And these points we took all falling into the straight line. Okay, I remember that when you plot your graph, I forgot to say that when you plot your graph, it's not a must that all the points will fall into the straight line, because there's bound to be experimental errors. So have 5 points plotted you can see them, and then you now use your ruler to find out which of the points are close, which of the points will give you a maximum straight line. And from here we'll have about 3 points that are close to the that are almost in a straight line. So we join these 3 points. So and ignore the other 2, which could be to experimental error. You don't force these 2 into the graph. So you try as much as possible to get the highest number of points and join them with a straight line, and ignore the one that could not fall into the straight line. Then you now draw a right angle triangle to take your slope. So on the vertical axis now, the value there is, if you go down, is 0.30. Then the higher value on the V axis is 0.30, while the lower value from where we took our slope is 0.075. So on the horizontal axis, when you go down, we're having 0.35 here. That is U axis, and then from this other end, we'll have a 0.10. See where I put our slope. So our change on vertical horizontal axis is going to be 0.35 minus 0.10, while our change on the vertical axis will be 0.30 minus 0.075. So let's go to the calculation. So you can see our slope, which is change on V axis over change on U axis, which should be 0.30 minus 0.75 Newton all over 0.35 minus 0.1 Newton. So it is 0.30 minus 0.075. The error is corrected. 0.30 minus 0.075 on the vertical axis, not 0.75. All over 0.35 minus 0.1 with the change on the horizontal axis. So we'll subtract the numerator and the denominator and divide the values to have 0.90 as our slope. 0.90 as our slope. The question now is, what does the slope represent? The slope we got as 0.90. The slope represents the relative density of the liquid. The liquid L is kerosene that are given to us. The liquid L is kerosene. So how do you know that the slope represents the relative density of the liquid? Remember the relative density given by upthrust of solid in liquid all over upthrust of solid in water. And what we plotted was V against U, where V is the upthrust of solid in the liquid kerosene and U is the upthrust of the solid in water. So that is our slope, and that is the relative density, which we got as 0.90. So we want to evaluate our accuracy. How do we evaluate whether we are right or wrong in this experiment? The standard relative density of pure kerosene is 0.80. The standard relative density of pure kerosene is 0.80, and we're getting 0.90. So within the limit of experimental accuracy, we are right, because 0.80 plus or minus 0.1, limit of accuracy, 0.80 minus 0.1 gives us 0.70. 0.80 plus 0.1 gives us 0.90. So within the limit from 0.70 to 0.90, we are correct. Because sometimes the kerosene may not be pure, and that may affect you getting exactly 0.80 as your slope. Mind you, you may be asked to find the slope, you may be asked to plot U against V. So you can try that one on your own instead of V against U. If you plot U against V, you're going to get a slope. If you find the inverse of that slope, that will now give you the relative density of kerosene. So if you plot U against V, that is this. You plot U against V, that is the slope now becomes changing U against changing V. Your answer will be the inverse of 0.9. Now, so whatever it is, if I had the inverse of 0.9, that gives you the relative density of a kerosene. So we'll go to the next question. Question S says, state two precautions taken to ensure accurate results. State two precautions taken to ensure accurate results. The precautions are: 1. I avoided splashing of the liquids by carefully dropping the masses into the provided liquids. I repeat, I avoided splashing of the liquids by carefully dropping the masses into the provided liquids. Number 2, I cleaned each mass before dropping it into any liquid to prevent contamination of the liquids. I repeat myself, I clean each mass before dropping it into any liquid to prevent contamination of the liquids. And also a top precaution, I avoided Parras error in reading the spring balance. Repeat, I avoided Parras error in reading the spring balance. So any of these two can serve as precautions. Question BI says, state Archimedes' principle. State Archimedes' principle. That's question BI. Archimedes' principle states that when a body is partially or completely immersed in a fluid, it experiences an upthrust which is equal to the weight of the fluid displaced. Repeat. It states that when a body is partially or completely immersed in a fluid, it experiences an upthrust which is equal to the weight of the fluid displaced. That's Archimedes' principle. Question BII says, a piece of brass of mass 20.0 grams is hung on a spring balance from a rigid support and completely immersed in kerosene of density 8.0 times 10 to the power 2 kilogram per meter cube. Determine the readings of the spring balance. Density of brass equal to 8.4 times 10 to the power 2 kilogram per meter cube. Repeat myself. A piece of a brass of mass 20.0 grams is hung on a spring balance from a rigid support and completely immersed in kerosene of density 8.0 times power 2 kilogram per meter cube. Determine the readings of the spring balance. Density of brass equal to 8.4 times 10 power 2 kilogram per meter cube. We'll go to the solution. MB, meaning mass of brass, given to us in the equation is 20 grams. We convert this mass to kilogram by dividing by 1000 to standard unit. That gives us 0.02 kilogram. dB, meaning density of brass, given to us in the bracket, is 8.4 times 10 to the power 2 kilogram per meter cube. Having done that, we have to find the volume of the brass. So for the relationship between density, mass, and volume, volume of a brass equal to mass of brass all over density of brass. So we substitute. The mass of brass is 0.02 kg. Density of brass given above is 8.4, that's power 2. We'll divide this to have 2.38, that's power minus 5 meter cube. That's the volume of the brass. Having done that, density of kerosene given to us, that is dk, in the equation is 8.0 times 10 to the power 2 kilogram per meter cube. They will have to find the upthrust of brass in the kerosene. Upthrust U given by volume of brass times density of kerosene times G, that's acceleration due to gravity. Substitute the values. Volume of brass is what we obtain above as 2.8 power minus 5 times density of kerosene given to us as 8.0 times power 2, and the value of your acceleration due to gravity is approximately 10. So multiplying these values together, 2.38 to the power minus 5 times 8 to the power minus 2 times 10, that gives us approximately 0.19 Newton, that's the upthrust. Then we'll find the weight of brass in air. The weight of brass is mass of brass times acceleration due to gravity. That gives us 0.02 times 10, which gives us 0.20 Newton. So the reading of the spring balance, with the tension on the spring, will now be weight of the brass in air minus upthrust. The weight in air will obtain it as 0.20, which is 0.20 minus the upthrust, which obtain as 0.19 minus 0.19, that gives us 0.01 Newton as our final answer. There are also some relevant questions that may still come out from this experiment. Maybe asked to sketch a diagram showing the forces acting on the body when immersed in water. So you can see the diagram showing the object immersed in water through the spring balance. So what are the forces that are acting on the object? So the forces are represented using those letters T, U, W. This is water. So you have to state what T, U, and W represent. T is the tension on the string, U is the upthrust, and W is the weight of the object, which is mass times acceleration due to gravity. So you can see that clearly. Okay. You can also be asked to scale the forces acting on the object when immersed in not water this time around, but kerosene or oil. We know that kerosene or oil are more viscous than water. So when immersed in water, we have to neglect the effect of viscosity because water is not all that viscous. But kerosene is viscous and oil is even more viscous. So you look at the diagram, the same kind of diagram that we have for water. We have T, the tension, we have U, the upthrust, we have W, the weight acting downward. Remember that upthrust act upwards, tension act upwards, but weight acts downwards. So look at the direction of the arrow in both diagrams. But we'll introduce another force now, or a fourth force called V. That V is not velocity. That V is called viscous drag. So we'll have the values T for tension, U for upthrust, W for weight, and V for viscous force or viscous drag. Somebody can ask you also to state the principle of flotation. What the principle of flotation or the law of flotation, which states that a floating object displaces its own weight of the liquid in which it flows. A floating object displaces its own weight of the liquid in which it flows. Or a body will float in a liquid if the upthrust exerted on it by the liquid is equal to the weight of fluid displaced. A body will float in a fluid if the upthrust exerted on it by the fluid is equal to the weight of the fluid displaced. So this is the principle of or law of flotation. Then what are the factors governing flotation of a body? What factors affect flotation of the body? Talk about upthrust, talk about the weight of the body, you talk about the shape or the geometry of the body. So these are the factors that govern flotation. And then that is it. So let's move to the next step. Okay, now we want to look at how we can obtain the values by calculations. So this aspect is to help those students that are in rural areas, the villages, whereby their schools lack equipment for this experiment, and they're also writing this examination. So how can they be able to obtain the values when they don't have equipment or standard equipment, or even their spring balance is not working very well? So how can they write the examination? So we decided to help them by showcasing how they can calculate the values on the table and get an approximate answer or an answer that is also acceptable. So estimating the data by calculations. Before we go to calculation, there's some formula you as a student should master. There's some facts you should know. So here I would say the average density of galvanized iron mass at room temperature is equal to 7.87 gram per cm cube. So the mass we use in this experiment is a galvanized iron mass. Galvanized iron mass, which is a common mass used in most school laboratories. Even if you're using steel, steel, the density of steel is around 8.4 gram per cm cube. Then if you're using the density of steel is around 7.9 gram per cm, almost equal to that of galvanized iron mass. If you're using brass mass, the density of brass is about 8.4 gram per cm cube. So the object you are using does not matter. Whether you're using iron mass for the experiment, you're using steel for the experiment, or using brass for the experiment, it will not affect your result. So for this calculation, we are using the density of galvanized iron mass at room temperature to be equal to 7.87 gram per cm cube. And this density will remain constant because density is a constant property of matter. It remains constant all through the experiment, will not change, remains constant all through the calculation. So now you look at U from the experiment. U is the upthrust of solid in water. Upthrust of solid in water. So how to find U? U is W1 minus W2. Remember that W1 is the weight of solid in air as given the experiment. And W2 is the weight of solid in water. So upthrust in water, U, is W1 minus W2. They will still have another formula for finding upthrust in water, U. We use Vs. That Vs is the volume of the solid, which you're going to calculate, times dW. That dW is the density of water, times G. That G is acceleration due to gravity, over 1,000. Why over 1,000? Because the volume of the object is expressed in cm cube. The density of water is expressed in gram per cm cube. So that 1,000 converts the gram to kilogram and bring everything to standard unit. So the density of water is 1.0 gram per cm cube, which is the standard value. And we're using that acceleration due to gravity as 10 meter per second squared. So this formula is very important before we go to the calculation. Also, we now look for V. V is given to us in the table, in the experiment, and V is the upthrust of solid in liquid L. And that liquid L is kerosene. And you know that upthrust is the weight of solid in air minus the weight of the solid in liquid. So that V also, just like we did for U, that V is the upthrust in water, while V is the upthrust in kerosene. So V becomes W1, that the weight of solid in air, minus W3, weight of solid in kerosene. So having done that, we also introduce that formula for V, which is the upthrust in kerosene, as Vs, similar to that the one we use as for U. Vs that times dk. Vs the volume of the object of the solid, dk density of kerosene, then times G. G is the acceleration due to gravity, over 1,000. Density of kerosene, standard value is 0.80 gram per cm cube, and G is 10 meter per second squared. So let's now go to the calculations. So before then, the weight of the solid in air, that W1, which is used in both calculations, is obtained by using mass of the solid times acceleration due to gravity. Mass of the solid in kilogram times acceleration due to gravity. So that is W1. We now start the calculations for the weight in air, W1, and also for the upthrust of each mass, on each mass, the upthrust in water and the upthrust in kerosene. So we have to first of all calculate the weight of the objects in air and find the upthrust in water, U, and the upthrust in kerosene, V, by these formulas, and then record on the table first. Now, for the 50 gram mass, our mass is 50 grams. We'll find the weight in air, which is W1, which is mass of solid, that's ms, in kilogram, times acceleration due to gravity, which is G. So 50 gram in kilogram is 50 over 1,000, and that gives us 0.05. Then times our G, which is 10, that gives us 0.50 Newton. So this 0.50 Newton represents the weight of the solid 50 gram in air. So go to our table and record it. So you can see serial number 1, experiment 1, the 50 gram mass here, ticked, and the weight in air 0.5 also ticked, recorded under W1 by calculation. Next, we obtain the volume of solid of the 50 gram mass, which is Vs. Vs given as ms over d. That is mass of the solid in mass of the solid in grams over the density of the ion mass, also in gram per cm cube. So mass of solid is 50 grams, and density of the solid is 7.87 gram per cm, which is given initially as a standard. Then the solving will have 6.35 cm cube at the volume of the solid, 6.35 cm cube at the volume of the 50 gram mass. Then we'll have to find the upthrust in water. The upthrust in water is volume of solid times density of water times acceleration to gravity over 1000. So we now have the volume of the solid is 6.35 times density of water is 1 times acceleration to gravity, which is 10 over 1000. So 6.35 times 1 times 10 over 1000 gives us 0.0635 Newton. 0.0635 Newton. That becomes the upthrust of the solid in water. So we'll go to the column for upthrust of solid water and record 0.0635 Newton. So you can see the upthrust of the solid in water recorded for you as 0.0635 Newton. So what I was saying, after recording the mass and the weight, the next is to find the upthrust before you start talking about W1 and W2 and W3. You find the upthrust in water by calculation 0.0635 Newton. The next is to find the upthrust of the solid in kerosene using V, that is V from the equation. We now use volume of solid times density of kerosene times G over 1000. The volume of solid remains 6.35, the 50 gram mass. Density of kerosene is constant 0.80 times G 10 over 1000. And that will give us 0.05080 Newton. Record our result. So look at the V column. The upthrust of the solid is recorded there in kerosene as 0.05080 Newton. So having obtained these values, we'll now talk about how to obtain W2 and W3. To obtain our W2, we know that upthrust in water is W1 weight in air minus weight in water, while W is the weight in water, which we are looking for. You make the weight in water, W2 solve the formula, we now have W2 equal to W1 minus U. Then our W2 now becomes the weight in air 0.5 minus 0.0635. And that will give us the value 0.4365 Newton for the 50 gram mass. So that's why you have under W2 0.4365. 0.4365 there as the weight in water. So we'll now talk about how to obtain weight in kerosene. So the upthrust V means the upthrust in kerosene equal to W1 minus W3 as given in the table or in the equation. We'll now make W3 the subject. The W3 is the weight in kerosene. W3 now becomes W1 minus V. Now for this 50 gram mass, our W1, the weight in air is 0.5, and our V, we calculated it to be 0.05080. So 0.5 minus 0.05080 gives us 0.4492. So this becomes the weight in kerosene, or the apparent weight in kerosene as W3. So you go to the table and see the record on W3 is 0.4492. 0.4492. So you see the order, how the values came in calculation. Mass recorded, weight in air recorded. After you got in weight in air, you first calculate the up thrust in water using volume of object times density of water times G over 1000. Also, you calculate the up thrust in kerosene using volume of object times density of kerosene times G over 1000. After you obtain U and V, then you can now make W2 the subject here. W2 now becomes W1 minus U. From there, you can get to your subject and you can get to your W2. Likewise, you make your W3 the subject. The W3 now becomes W1 minus V. You can now find your W3 for the 50 gram mass. So the same process is what we're going to use for the other ones. I'll do 1, 2, and 3 while you try the other ones on your own. Now move over to the 100 gram mass. For the 100 gram mass, M is 100 grams. Then we'll have to convert that mass to weight to find the weight in air, W1, as we did for the 50 gram mass. So the weight in air is mass of the solid in kg times acceleration due to gravity, that is G. The mass of the solid in kg, convert that 100 gram to kg, divide 100 gram by 1000, that gives us 0.1 kg. Then times the value of G, which is 10, it gives us 1.0 Newton. So let's look at the table. So you can see experiment serial number 2. Mass of the solid in air is 100 grams. Tick there. And then the weight in air, W1 is 1.00 Newton, also ticked. So next is we're going to do for the calculation of the up thrust in water and the up thrust in kerosene. Before we look for the up thrust, we have to first of all find the volume of the object as we did for the other one, for the 50 gram mass. But this time around, we're working with the 100 gram mass. So volume of the object or solid is mass of the solid all over density of the solid. Mass of the solid is 100 gram in this case, and density remains constant. No matter the mass, density remains 7.87 gram per cm cube. So divide 100 gram by 7.87 gram. You have 12.71 cm cube at the volume of the object. Having obtained the volume of the object, we'll now go to calculate our up thrust in water using volume of the object times density of water times G over 1000. So volume of the object is 12.71 cm cube. Density of water is 1 gram per cm cube. Our central degree of gravity is 10 all over 1000. If we solve this, we're going to have 0.1271 Newton. Record on the table. So we can see the up thrust in the second row, U of water on the object, which is 0.121271 Newton. We'll now find the up thrust of kerosene on the object that we'll do for V now. To get our V, we use volume of solid times density of kerosene times G over 1000. Remember that V is the up thrust in kerosene. So volume of the solid is same volume calculated above, 12.71 times density of kerosene, which is 0.80, times G, which is 10 over 1000, and that gives us 0.1017 Newton. So we'll look at our report there. Under V, the second row, the up thrust in kerosene, that is V, is 0.1017 Newton marked. So we'll now go over to find our W2, the weight in air, and then weight in kerosene. So applying similar method I used before. Up thrust is weight in air, W1 minus W2. Up thrust in water is weight in air, which is W1 minus weight in water, which is W2. We want to find W2, make W2 the subject, which is W1 minus U. The weight in air for the 100 gram is 1.0. The up thrust in water calculated is 0.1271. You subtract, you get approximately 0.8730 Newton. 0.8730 Newton. So I have a reading recorded there as 0.8730 Newton as our weight in air. So let's now find our W3. To get our W3, we now have V. That V is the upthrust in kerosene equal to W1 minus W3. We now make W3 the subject. W3 is the weight in kerosene. W3 becomes W1 minus V. It's going to be 1.0 minus 0.1017. And that gives us 0.8980 Newton. 0.8980 Newton. So that becomes the weight in kerosene. So record our W3 as 0.8980 Newton. So we'll try one more example for number with there is the third experiment or the third calculation. Then you do the remaining 4 and 5. So now move over to the 150 gram mass. The mass is 150 gram. We'll find the weight in air first, W1, using mass of the solid in kilogram times acceleration due to gravity. You convert the mass to kg, divide by 1000, that gives you 0.15. Then multiply by g that is 10. Why should we convert the mass to kg? Because the value of g is already in standard unit, meter per second squared. So uniform units must work together. So 0.15 times 10, that gives us 1.5 Newton as the weight in air. So report our work on the table. So now I have for the third experiment the mass 150.0 gram, and then the weight in air is 1.50 Newton obtained. So the next is we'll go over to calculate our upthrust in water and our upthrust in kerosene. And before we get the upthrust, we'll first of all find the volume of the object that we use in the calculation. So volume of the solid is mass of solid over density of solid. Remember, in this calculation of volume, we don't convert to SI unit. We retain the mass in gram. We only convert to SI unit when we are calculating W1. The mass will now go to kilogram. So why should we retain the mass in gram? Because the density is in gram per cm cube. So the mass of the solid here is 150 gram, and the density being constant is 7.87 gram per cm cube. When we divide these, we'll have 19.0 cm cube. So this is the mass, 19.06 cm cube, the mass of the volume of the 150 gram mass. Having done that, we now obtain the upthrust in water, which is one of the solid and density of water times acceleration due to gravity over 1000. So we have the volume of the solid as 19.06, density of water as 1, then the value of our G as 10 over 1000, and that gives us 0.1906 Newton at the upthrust in water. So we report our work, the upthrust in water as 0.1906 Newton. So we'll go over to find the upthrust in kerosene by calculation. The upthrust in kerosene, which is V, again by volume of solid Vs, times density of kerosene dk times G over 1000, and that will give you 19.06 times density of kerosene 0.8 times 10 over 1000. We now have 0.1525 Newton as the upthrust in kerosene. So let's report our work. So we have the upthrust in kerosene reported here as 0.1525 Newton. So we'll now go over to find our weight in air, W2, and the weight in kerosene, W3. So weight in water, W2, is equal to W1 weight in air minus upthrust. So for the data we generated, we have weight in air 1.5 minus the upthrust in water 0.1906, and that will give us 1.3094 Newton. 1.3094 Newton. So let's go to report the work. So you can see the value of the weight in air W2 on the third column as 1.3094 Newton. 1.3094 Newton. So let's find the apparent weight in kerosene. So the weight in kerosene, W3 is W1 weight in air minus upthrust in kerosene. So the weight in air is 1.5. The upthrust in kerosene calculated is 0.1525. So 1.5 minus 0.1525 will give us 1.3475 Newton. 1.3475 Newton. So you can see the reading recorded for you. 1.3475 Newton. So you can calculate, use same principle and calculate remaining ones. So let's run through the readings now. So look at the table, calculated data. So the same heading, serial number, mass in gram, weight in air, W1 Newton, weight in water, W2, weight in kerosene, W3, upthrust in water, W1 minus W2 Newton. The same table we had before, upthrust in kerosene, V, W1 minus W3 in Newton. Then, when the mass is 50.0 grams, the weight in air is 0.50 Newton. The weight in water is 0.4365 Newton. The weight in kerosene is 0.4492 Newton. The upthrust in water is 0.0635 Newton. The upthrust in kerosene is 0.05080 Newton. When the mass is 100 grams, the weight in air calculated is 1.0 Newton. The weight in water is 0.8730 Newton. The weight in kerosene is 0.8980 Newton. The upthrust is in water 0.1271 Newton. The upthrust in kerosene is 0.1017 Newton. Then for the third one, when the mass is 150 grams, the weight in air is 1.500 Newton. The weight in water is 1.3094 Newton. The weight in kerosene is 1.3475 Newton. The upthrust in water is 0.1906 Newton. The upthrust in kerosene is 0.1525 Newton. When the mass is 200 grams, the fourth experiment, the weight in air is 2.00 Newton. The weight in water is 1.7459 Newton. The weight in kerosene is 1.7967 Newton. The upthrust in water is 0.2541 Newton. The upthrust in kerosene is 0.2033 Newton. Then the last mass, when the mass is 250 grams, the weight in air is 2.5 Newton. The weight in water is 2.1823 Newton. The weight in kerosene is 2.246 Newton. The upthrust in water is 0.3177 Newton. And the upthrust in kerosene is 0.254 Newton. Remember, we made some assumptions in the calculation. The density of the object is, we took it as 7.87 grams per cm cube. We have to record the mass first. Find the weight in air using mass translation to gravity. Make sure you convert the mass to kg by dividing by 1000 and multiply by 10 to get your W1. After that, we now got the volume of the object. The volume of the object is given by a mass, the mass in grams all over the density. Like for the 50 gram mass, the volume going to be mass, which is 50 grams over the density constant 7.87 grams per cm cube. When you're looking for the volume, don't convert to SI unit. When you're looking for the W1, convert the mass to SI unit. We're looking for the volume, use mass, 50 grams given to you over the density 7.87 grams per cm cube. After getting the volume of the object, then apply the formula for up thrust I gave to you. Up thrust is volume of object times density of the liquid. If it's water, is 1.0. If it's kerosene, is 0.8 times G, which is 10 all over 1,000. You get the up thrust in water and get the up thrust in kerosene. Then you can now, after doing this, you now solve for W1, W2. W2 from this formula is given as W1 minus U. And then for W3, you get W3. W3 is given as W1 minus V. So you substitute and then you solve all through. You're going to get these values and compare your values. Okay? Having done that, are these experimental data good to be presented in the exam hall? No, they're not good. Because you need to still make some approximation before you use them as real data. So as I said, for us to use those values as real data, we need to make some approximation. So let's see what we have here. They say the spring balance gives digits to 2 decimal places and can give to 3 decimal places. That if the last digit is 5, that if you approximate, they say the pointer is between 2 values. Somebody can say 5, in between, that is half of 2 values. So the above data cannot serve as an experimentally derived data unless there are some modifications and approximations as shown below. So these data, the values in W2, W3, U, and V may not serve as experimental data because they look awkward. So the spin balance cannot give all these, not all that sensitive to give these kind of values. So let's see how we can approximate. We'll keep M and W1 constant. The M and W1, they're okay. The values on M and W1 column are okay. No change. 50, 100, 150, 200, 250, 0.5, 1.0, 1.5, 2.0, and then 2.5. We're trying to make them look real. Then going to W2 column. You see, when you are now approximating, you have to get M, W1, W2, W3 before you look for U and V. But when you're calculating, you get your W1M and W1 ready and get your U and V ready before you look for W2 and W3. In approximation, you have to get the M, W1, W2, W3, and then do U and V last, so you don't make mistake. So go to W2. To W2, you have 0.4365 there. 0.4365 as the value calculated. So let's go what we have. We have 0.44, an approximate to the 2 decimal places. 0.44 there. So we now go to W3. We have 0.4492. We now go to the actual value or real value. We have 0.45 taken to 4SF. See the approximation we are doing. Now to get your U and V, you don't get these ones from the table again because you have done approximation. To get your U and V, you do it from here. Your U becomes W1 minus W2, which is 0.5 minus 0.44. And then you approximate what you get to 0.5 minus 0.44. You approximate what you get, 0.0600. Then for V, which is W1 minus W3, W1 is 0.5, W3 is 0.45, and that gives us 0.0500. So I think to get your up thrust and V, you don't necessarily approximate because these ones are obtained by calculation. They are not being measured. So whatever you get, you write it down. So to go to 100 gram mass, the 100 gram mass and the weight are brought down like that, the way they are, no change. I told you that the mass and the weight sections will be the same. Then to get our W2, we'll now move up there. W2, we got 0.8730. the spring balance will always give you to around 2 decimal places. So that 3 is not significant. So we'll remove it and have 0.87, approximately 0.87 as an approximate from the spring balance. Then our W3 is 0.8980. So to 2 decimal places, we have 0.90. So record 0.90024 SF. Now to get our up thrust in water, W1 minus W3, these ones don't need approximation. W1 is 1 minus W2, sorry, 1 minus 0.87, W1 minus W2, that gives you 0.13. To get our up thrust in fluid, W1 minus W3, that becomes, W1 is 1.0, W3 is 0.9. So 1 minus 0.9 gives us 0.100. So for the 150 gram mass, the weight remains 1.5, the mass remains 150, no change. Then W2 and W3 should be approximated. So going to W2 value there, we have 1.3094 to 2 decimal places, 1.30. We can ignore the 1 because it cannot measure to 1.31. So 1.30 is okay. So we'll have it there. So W3, we'll have 1.3475. And then we can have 1.35 as an approximate. 1.350. To get our U, W1 minus W2, W1 is 1.5, W2 is 1.3. We'll subtract, we'll have 0.200. To get our W3, our V, sorry, W1 minus W3, which is, our W1 is 1.5, W3 is 1.35. So 1.5 minus 1.35 will give us 0.15. Go to the fourth column, 200 gram mass, weight in air 2.0 Newton, the same as in the table above. Then we're going to approximate W2 and W3 very well. So W2 value is 1.7459. We'll take 1.75 to 2 decimal places, ending with 5. So to get our W3, we'll have 1.7967. We'll take 1.80 to 2 decimal places. To obtain our U and V, that is done by calculation. Our U will now become W1 minus W2, that is 2 minus 1.75. That gives us 0.25. Our V is W1 minus W3, which is W1 is 2, W3 is 1.8. So 2 minus 1.8, that gives us 0.20 Newton. Also, going to the last column, 250 grams mass, and then W1 is 2.5 Newton. So we'll now approximate W2 and W3. Our W2 is 2.1823. Through the map places is 2.20. We'll have it there. And then W3, 2.246, which you take it to 2 decimal places, 2.25. Approximately that value. Then we'll now get our up thrust, weight in air minus weight in water, which is weight in air is 2.5 minus 2.2, that gives us 0.300. Then the up thrust in kerosene, W1 minus W3, that gives us 2.5 minus 2.25, and that gives us 0.25. So you can see your data. So this data look real. You can't use this one like that. So it looks real. So we can compare this data to the actual experiment that we did and see whether they rhyme or whether they are similar to each other. So you can see for the calculated data, the mass and the weight in air remain the same. 50, 0.5, 100, 1.0, 150, 1.5, 200, 2.0, 250, 2.5. And for the experimental data, the mass and weight remain also the same thing. There's no change in mass and weight column, because these ones are taken as being fixed values. So for the calculated data, W2, the weight in water, we have 0.44 for the 50 gram mass and 0.87 for the 100 gram mass. We'll now go to the experimental data. The one would go by experiment. Our W2 is 0.4 as against 0.44 for the calculated data, 0.85 as against 0.87 for the calculated data. This is the experimental data. Okay. So we'll go to the experimental data again. We'll go down the experimental data for the 150 gram. The weight in water is 1.3 grams. And then the weight for the 200 grams, the weight in water is 1.75. And that is for W2. 1.3 and 1.75. We'll now go to the one calculated. The one calculated for the 150 gram, the weight in water, W2 is 1.35 as against 1.30 as against 1.35 that will go for the real experiment. While the 200 gram, the calculated value, the weight in water is 1.775, which is the same thing as to, okay, we got at the same thing as we got for the real experiment. Okay, we got the same thing. One for the 150 gram, 1.30 for the calculated data, and then the 200 gram 1.75 for the 200 gram, the weight in water for W2. This is for the calculated data. Then for the experimental data, we got 150 gram, we got the same 1.3, same thing in water, and also the 200 gram, the same 1.75 grams. So the values agree here. Then we'll now go for the 250 gram. The weight in water for the real experiment is 2.150, while the calculated value for the 250 gram will have 2.2, just an approximate. You can see that the readings are agreeing. Now, for the weight in kerosene, W3, for the calculated data, we have 0.45 and 0.90 and 1.35 for the first three stage. That is 50, 100 gram, and 135 gram. Let's go to the real experiment. For W3, we have 0.425 as against 0.45 for calculated, 0.875 for real experiment as against 0.9 for calculated, and 1.35 for the real experiment as against, okay, the same thing for this one, 1.35 for the 150 gram, that the weight in kerosene, and also for the calculated data, we also have the same 1.35 Newton. Then going to the 200 gram and the 250 gram, the weight in kerosene, 1.8 for 200 gram and then 2.25 for 250 gram. So let's go to the one calculated. For the one this is the one calculated, please. Let's go to the one that is done by experiment. So by experimental analysis, the weight for the 200 gram in kerosene is 1.80. The same thing for the one calculated. Why the weight of 250 is 2.20. What the calculator gives us 2.25. So you see that the readings are comparable. Now let's look at the upfronts. This is for the live experiment. 0.10, 0.15, 0.20 for the first 50 gram to 150. Then the upthrust in water for the this one is for the one with red light for the real experiment, 0.15, 100, 0.15, 0.2 for the upthrust in water. We now go to the calculated values, 0.06 as against 0.1, 0.13 calculated for 100 gram as against the real value of 0.15, then 0.20 for the top value, which is same thing as the one we got for real experiment as 0. Okay, let's look at the value again. 0.10 for the first one, did the real data, the real experiment. The calculated one gives us 0.06. The second one, 0.13. Then the real experiment gives us 0.15, slight variation. Third one gives us 0.20, upthrust in water. The real experiment gives us the same 0.20, the same thing there. The fourth one gives us 0.25, the upthrust in water, while the real experiment gives us, for the fourth one, the same 0.25. Then the reference, the fit one 0.35, and then the calculated one gives us the same, gives us 0.3, just slight differences. Then our ultras in kerosene, for the calculated value, the first one gives us 0.05, while the real one gives us 0.075. Then the calculated value gives us, second one for the 100 grams, 0.10, while the real one gave us 0.1250. Then the third experiment, the calculated value gives us 0.150. The real one gives us the same thing as 0.150. Then the fourth experiment, the ultras in kerosene is 0.20. The real one gives us the same 0.20. Then the one calculated, we have the fourth, the fifth experiment 0.25, the ultras in kerosene, while the real one gives us 0.30. You see that the readings are comparable, very similar and very close to each other. So let's look at the graph we're going to obtain from the calculated values when we plot V against U and compare the nature of the graph and their slopes. So this is the plot of V in Newton against U in Newton, upthrust in kerosene against upthrust in water. And we'll show the same kind of scale because the reasons are similar. I see the shape of the graph, they look alike. Except that in this one that we got by a real experiment, the values are very close. I mean, they appear to be almost entering the straight line. So you can see, after plotting, we'll have this. The scale we chose, the sentence 0.05 to 2 cm on the vertical axis, that the V axis, the ordinate. And then we also chose 0.05 to also 2 cm on the horizontal axis or on the abscissa, the horizontal axis. Plotted as I explained before. We got also a straight line graph. The values would have fallen into the line if not for the approximations that we did. So what we plotted was the values to obtain by approximation, that is this value. That is the values we plotted, not the other one. The other one is not what we use. So V against U, you obtain this graph. Then we took our slope, taking the 2 points that fall into a straight line, the fourth point and the last point, and we took our, the 4 point and the second point. So we took our slope on the V axis 0.20 and then 0.1. That is the coordinates on the vertical axis. Then the horizontal axis will have a 0.25 and 0.13. So we took our slope and then let's see what we got. So our slope goes thus: change on V axis all over change on U axis. The coordinates on the V axis 0.2 minus 0.1. The coordinates on the horizontal axis 0.25 minus 0.13 Newton. So Newton cancels Newton. The slope has no unit, as in the first one we did. That gives us the numerator, if you subtract, have 0.10. The denominator have 0.12. So 0.10 divided by 0.12 gives us 0.833. So this one gives us a closer value to the real value for the relative density of kerosene, which is 0.8. So why is this one very close to the real value? Because it's done by calculations. So you see this. To help our brothers or sisters who are in local schools or who are in the villages, let me not call it local schools, who are in the villages that don't have equipment to run this experiment. So having done that, we have come to the end of this alternative to practical instruction or demonstration of the experiment for number 1 question on alternative to practical physics, May, June 2024, which is on upthrust or fluid mechanics, upthrust, demonstrating Archimedes' principle. So if you are not subscribed to the channel, please tap on the subscription button. We thank our subscribers, and then those who are commenting and asking questions. We also appreciate you guys. If you are not answered your questions, we're going to answer it, please. Keep on viewing, stay connected to the channel. You can only see our videos. Even if there's any error I want to correct, or there are certain things we want to mention, we are going to do that on the YouTube. And if you're not a subscriber, you're one that just come in and run away. You'll not see anything. But you're a subscriber, once there's anything mentioned, or when there's any information given, you'll see it because you're a subscriber. So continue, share videos to friends, and then to classmates, to WhatsApp groups, and then to teachers also. We also help you understand, explain more. And schools that are well equipped, like private schools, you can shoot our videos on projector. You have projector lantern where students can look at the videos and see how the experiment is done, see the precautions carried out, and then before they do their own. I think when you watch videos very well, you get used to it more than you just enter the lab and start using equipment that you're not even sure of, or you're not done before. So that's a simple experiment, number one. And I expect everybody to get the full mark for this number one. So in our next attempt on this YouTube, we're going to number two, physics experiment that has to do with rectangular block, prism. That is refraction of light. And then we can still talk about number three, which is the meter bridge, the electrical experiment. So stay connected, and thank you very much for viewing.